Today, we are diving deep into the wild, high-stakes game of AI security. We're going to look at how a seemingly bulletproof defense for artificial intelligence was completely, utterly shattered, and what that tells us about the vulnerabilities hiding just beneath the surface of the tech we're all starting to rely on.
But first, let me ask you something to really set the stage. Picture a stop sign. Now, imagine someone makes a tiny, almost invisible change to it, maybe a few strategically placed stickers. To you, it still looks like a stop sign, but to a self-driving car, well, it might now read speed limit 85. And no, this isn't science fiction. This is the very real problem we're going to unpack today.
Take a look at these images. What's so crazy is how normal they all look, right? On the left, you've got some handwritten numbers. On the right, everyday things like a school bus and a dog. But here's the twist. With tiny, targeted manipulations that you and I would never notice, a neural network can be tricked into seeing something completely different. A 3 becomes a 7. A dog becomes an ostrich. This right here is the invisible threat of what we call adversarial examples.
So, to really get our heads around how these attacks work, we first need to get a solid handle on what this invisible threat actually is.
Okay, so here's the official definition. An adversarial example is an input, like an image or a sound file, that has been just slightly and very maliciously tweaked. It's been specifically engineered to fool an AI into making a mistake, all while looking totally normal to us. And believe me, the stakes here are incredibly high. We're talking about the potential for self-driving cars to be sent into the wrong lane, or for malware to hide itself from antivirus software just by changing a few bits of its own code. Attackers could even embed secret voice commands into a song to take control of your smart speaker. The potential for real-world harm is exactly why there's this huge race to build better AI defenses.
Now, to craft these adversarial examples, researchers have a few different strategies. You can think of them as different ways to be sneaky. An L0 attack is like a sniper. It changes the absolute minimum number of pixels it can get away with. An L2 attack is more like adding a really faint, almost invisible layer of static over the entire image. And then there's L infinity, which is kind of like a budget-based approach. You can change as many pixels as you want, but you can't change any single pixel by more than a tiny, tiny amount. So, facing this growing threat, a group of researchers developed what really seemed like a breakthrough solution, a way to make these AI models totally robust against attacks.
It was called defensive distillation, and the idea behind it is actually pretty brilliant. First, you train a teacher network, but instead of that network just saying, yep, that's a dog, it gives you a breakdown of probabilities, like I'm 90% sure it's a dog, but there's a 5% chance it's a cat and a 5% chance it's a wolf. Those are the soft labels. Then, you take a second student network and train it on those much more nuanced labels. The whole theory was that this process would smooth everything out and get rid of the little blind spots that attackers were exploiting.
And you know what? At first, it worked. It worked unbelievably well. Attacks that used to have a 95% success rate were stopped dead in their tracks. Their success rate just plummeted to 0.5%. It honestly looked like the problem was solved.
The original paper on this was, as you can imagine, super optimistic. They basically said that defensive distillation beats all the attacks that existed at the time. For a moment there, the AI community thought they had their first truly effective defense.
But, as anyone in security knows, no wall stays unbreached for very long. A new group of researchers decided to take a much closer look, and what they discovered changed everything.
They went and built a whole new suite of attacks, more powerful, more intelligent attacks. And when they pointed these new weapons at the supposedly bulletproof, distilled networks, the success rate wasn't 0.5%. No, it was 100%. Every single time. They could craft an adversarial example that fooled the defense. So, how on earth did they do it? Well, they had a key insight. They realized the old attacks weren't failing because the network was truly secure. They were failing because they were attacking the wrong part of it.
So here's the critical flaw they found. See, most attacks work by looking at the AI's final answer and calculating how wrong it is. They use the direction of that error, what's called the gradient, to figure out how to tweak the image. But with defensive distillation, the model becomes so overconfident that its final probabilities are basically 100% or 0%. This makes that error gradient just disappear. It vanishes. The attack gets no signal, no direction to go. It's like trying to climb a hill that's perfectly flat.
The new attacks just sidestepped this problem completely. Instead of attacking the final, confident probabilities, they attacked something called the logits. You can think of logits as the model's raw, unfiltered thoughts before it makes its final decision.
And as you can see from this table, attacking those raw thoughts was 100% successful. The researchers found a much richer, much better signal to guide their attack, and it proved the defense was just hiding the vulnerability, not actually fixing it.
You see, the failure of defensive distillation wasn't just about one clever hack beating one clever algorithm. It actually revealed something much, much deeper about the fundamental nature of these neural networks.
It turns out these adversarial examples might not be some clever trick that exploits a weird, complex blind spot in the AI. The linearity hypothesis suggests they exist because, at a very small scale, even these incredibly complex networks behave in a surprisingly simple, linear way. That means a small, consistent push in just the right direction, that's the adversarial noise, can reliably nudge the AI's decision over a cliff, causing it to misclassify something. The problem isn't a bug, it's a fundamental feature of how they work.
And this slide right here is basically the smoking gun. In the original defense, you could turn up a dial called temperature during distillation, and it made the model seem more robust. But all it was really doing was making the gradients for the old attacks vanish even faster. When tested against the new, smarter attacks, changing the temperature had no effect on robustness whatsoever. The defense wasn't making the AI stronger, it was just breaking the old tools people were using to measure its strike.
But there's another, even sneakier way to break these defenses. It's called transferability. It's this bizarre, almost spooky property where an image designed to fool one specific AI model often fools a completely different one too, even one with a different architecture or a special defense. And this weird phenomenon is probably rooted in that same linearity hypothesis we just talked about. The attack is exploiting a fundamental weakness that lots of different networks share.
So, the attackers came up with a brilliant plan. They thought, forget trying to attack the tough, defended network directly. Instead, let's attack a simple, undefended one. But they didn't just create an example that barely fooled it. No, they used a special parameter called kappa to dial up the attack's confidence, creating an example that the simple model misclassified with extreme certainty. And then they just showed that super convincing fake image to the defended network.
And here's what happened. As you crank up that confidence dial, the kappa, on the simple model, the odds that that same image will also fool the defended, distilled model just shoots up toward 100%. This was huge. It proved that any truly effective defense has to do more than just resist direct attacks. It also has to break this property of transferability.
So what's the big picture here? What does all this mean? Well, it means we are right in the middle of a classic security arms race. For every new defense, you can bet a new attack is already being developed.
So here are the crucial takeaways from this whole story. First, you can't ever know if a defense is strong until you have hit it with the best possible offense you can imagine. Second, breaking transferability isn't just a nice to have, it's absolutely non-negotiable for a secure system. And maybe most importantly, this spectacular failure of defensive distillation wasn't really a setback. It was a critical, necessary lesson that pushed the entire field forward, forcing everyone to build stronger attacks, and from that, much, much stronger defenses.
And that leaves us with one final fascinating question to chew on. AI can already outperform us at incredibly complex tasks, yet it can be completely tricked by what is essentially invisible noise. If its perception is so powerful, yet at the same time so fragile, what does that tell us about the massive gap between artificial calculation and true, robust intelligence?